So we'll start here. It says in the picture below, a vehicle is maintaining a constant speed as they traverse the pictured roadway. Although the car travels at a constant speed, the car is able to successfully maintain contact with the ground. So this is telling us in the setup of the problem that there will be a normal force acting on the car throughout the car's journey through the road. On the diagram below, draw a free body diagram for the car when it's at the top of the hill and when it's at the bottom of the hill, or bottom of the dip. Be sure to indicate the direction and name of each force that acts on the car as well as their relative sizes. If a force is the same size at both locations, it should be clear from the diagram, and if a force is not the same size, it should also be clear in the diagram. Be sure to use the dotted lines to help assist you in your scale drawing. All right, this was pulled from a released AP exam. They're not going to tell you all of that information. I just want you to know that. They're just going to say draw a free body diagram for the car at those two places. So if you see dotted lines on a force diagram, you should know they are comparing sizes, and the size of the arrows is going to matter. If it's just an empty box, they're probably going to be less concerned with the size of the arrows. Does everybody understand? So, first thing I want to recognize is that at the top of the hill, the unbalanced force has to be downwards so that there can be an acceleration towards the center of the circle. And at the bottom of the dip, there has to be an unbalanced force upwards so that the acceleration can be towards the center of the circle. So I want to make sure that that is something that happens here in the free body diagram. I'm going to start by making sure I have an arrow that represents the weight for both cars that is the same size. And I want to make it long enough so that there is enough room for me to adequately demonstrate the size of the normal force at both locations. At the top of the hill, the unbalanced force has to be downwards. So I'm going to draw an exaggerated small arrow for the normal force so that it is clearly less than the weight. And at the bottom of the hill, I'm going to draw an exaggerated long arrow for the normal force to clearly indicate that it is greater than the weight. No ambiguity. I think they only gave 2 points for this actually on the actual AP exam. I think when I gave this as a test last year, I gave 3 points. I believe I gave 1 point for indicating the weights were the same, and downwards. And I believe I gave 1 point for showing a normal force that was less than the weight here, and 1 point for showing a normal force that was greater than the weight here. And I don't think there was anything about additional forces, because some people, I think, last year drew like applied force from the engine and friction on the car. And I think we just ignored any sideways forces that were acting on the cars.
Excuse me.
You're excused, I guess. I don't know if I have the power to grant you that, but I'll try. All right, any questions about that? All righty. When the car is at the bottom of the dip, the occupants of the car feel as though they are 1.5 times their normal weight. This is their so-called apparent weight. How fast must they be traveling? Be sure to show all of your work. We don't know the mass of anything in this problem, so I'm going to use M as the mass of things in this problem. They tell me the normal force is 1.5 times the weight. That is told to me in the problem, which means that the normal force is 3/2 mg. Any question about that? All right. How fast must they be traveling? Well, I do know that the unbalanced force is dependent on the speed because we're traveling in a circle. So I'm going to lay out that at the bottom of the dip, since up has to be positive, the normal force minus the weight has to be equal to MAC. There's probably a point issued for for knowing that this is a centripetal acceleration problem, and maybe a point issued for getting your net force right. I don't remember. I don't remember how I break the point. This whole FRQ was only, I think, 7 points on the actual exam, so they didn't give many points for some of the stuff. We're going to do a substitution here. I'm going to say that 3/2 mg minus mg equals MAC. I'm just substituting mg in for the weight and substituting what I know about the normal force. I am also going to make another substitution for the centripetal acceleration. All right. Now I think I can complete the question. I will notice that there's on the left, I can actually combine those. 3/2 minus 1 is just 1/2. So that's 1/2 mg. And that equals mv squared over r. I'll notice I have an m in every term on both sides, so I can factor it out and get rid of it, assuming it's not 0. And then I can show that it's g times r over 2 on the left equals v squared by multiplying both sides by r. And let's see, r is 20, g is 10, so 200 divided by 2 is 100, and the square root of 100 is 10 meters per second. That's the answer. Any questions about that? Alrighty. If the car had been traveling the same speed you found in part B number 1 when they rounded the top of the hill, what would be their apparent weight at the top of the hill? All right, well, top of the hill, net force is downwards, so I'm going to have weight minus normal equals MA. I'm looking for the normal force here. That's the apparent weight. And so it'd be nice to have it in terms of like mg somewhere along the line, but let's see what we can do here. I think I'm going to do some substitutions first, like mg minus normal equals m v squared over r. That all look good to you? All right. I'm going to solve this for normal, so I'll add n to both sides and then subtract mv squared over r from both sides and get mg minus mv squared over r equals normal. Now some folks in second period had trouble with what I'm going to do next, but I don't think it's asking too much. Bless you. mg minus mv is 10. We're using the velocity we got in the previous portion of the problem. So that'll be 10 squared divided by r, which is 20. Now I'm supposed to get the apparent weight. So I would really like this to be in terms of mg. But I have a number there, so let's see what that number is. Well, it's 5, right? 10 squared is 100, divided by 20 is 5. Isn't 5 just 1/2 g? Isn't that true? This is a mental leap going from here to here, but I think it's an appropriate one, because that way I can write my answer as normal equals 1/2 the weight. I don't know how much credit you would have gotten if you put 10 in for g there and said normal equals 5m. It's not really giving me a comparison to the weight, but I think that's not a particularly challenging mental leap to say that 5 is half of 10 and 10 is g. What? Okay. Any question about what I did there? Go ahead.
I understand how we got from mg minus 5 to mg minus 1/2 g, but could you reiterate how we went from that to n equals 1/2 W?
N equals mg minus 1/2 mg, right?
Right.
So that's 1 mg minus 1/2 mg. So isn't that 1/2 mg?
Yeah. Yes.
And then wouldn't that be just 1/2 the weight?
Yes.
Okay.
Thank you.
You're welcome. All right, next question. Explain using a clear and complete argument why there is a maximum speed at which the car can round the top of the hill. Your explanation should refer to physics principles and can reference equations, but your verbal argument must clearly state why each equation is being referenced and what part of the relationship is important to your discussion. All right, I'm going to use one relationship. I'm going to use weight minus normal equals m v squared over r, something that I got from the last bit of work. This is the net force relationship at the very top of the hill. Now, the first thing I'm going to try and indicate here is that looking at this relationship, weight doesn't change as we go over the hill. So, since weight doesn't change, as v increases, n must decrease. That's what that equation says. If the right side gets bigger, the only way the left side can get bigger is to make n be smaller, because I'm subtracting it. I believe you have to make this point. I think the next point is you lose contact when n goes to 0. I can't spell. This is the smallest n can be. Therefore, v is a maximum when n equals 0. I think you have to make all 3 points. I think there has to be acknowledgement that contact with the ground is based on having a normal force. I think there has to be an acknowledgement that there's a relationship between the normal force and the velocity. And I think you need to indicate clearly that your maximum for v is when the normal force is 0. Probably writing out is going to be one of the harder things you guys have to do on the test tomorrow. Question D is just fulfilling the rest of this. What is the maximum speed the car can go over the top of the hill without losing contact with the ground? That is executing on this idea. So we're going to start here. And our maximum is when the normal force is 0. So since weight is mg, cancel the m's. G is 10, R is 20. That's it. I think that's the end of that question. Any follow-up? Yep.
For the B one, for the first part, how come you do n minus w, and then for the second part, we do w minus n?
Well, in looking at these pictures here, I want to make my direction positive in the direction of the acceleration. So I'm making downwards positive here. And I'm making upwards positive here. Does that make sense? Do you need anything more than that? Okay. All right. One that's like this, where there will be more numerical information offered, so I'll have numerical answers. I think you can, so like I said, I think in class, I probably made some changes. Just one that I think is pretty clear. It says, a box in section A of the diagram has a mass of M, is on a plane, or I'm sorry, it's on an inclined plane that's inclined an angle theta with the horizontal. A light string connects the box to the top of the incline. The string is connected so that it is parallel with the incline, and the system is at rest. In the box on the right, draw a free body diagram for the box while on the incline. Well, without any other information, I think there's 4 arrows that have to be drawn. Weight, normal force, tension, and potentially friction. I'm not doing a great job drawing them, and on your test, you should use a ruler if you want to get full credit. They go on later in the problem to say that there's no friction on the ramp. I probably said in class last year to ignore friction in the beginning of the problem. So I think this is probably not supposed to be there. That's not what the problem states, though. So if you were doing this problem last night and you weren't sure, friction would have acted up the ramp. Static friction would have tried to prevent the block from sliding down the ramp. It would make it so that the tension would be potentially less than it would have to be because there's no friction. So, but I'm not trying to trick you tomorrow. Your test will be clear if there's friction or not friction. Does that make sense? I'll make it clearly a part of what you have to do. It says, how does the tension of the string change if the angle of the box is increased? Explain in a complete sentence or two. Look, this isn't a mathematical question. If the ramp increases, the tension points more upwards. It's that simple. The tension is pulling more upwards, it's holding more of the weight of the box. I mean, imagine it to its extreme, where the angle's 90 degrees and the box is here and the tension's up there. Wouldn't that be all of the weight of the box? And the other extreme is if the incline is here and the box is there and the tension's this way. That'd be none of the weight of the box. So I would make a reasoned discussion and simply state that as the ramp increases, the tension points more upwards, thus holding more of the weight of the box. This is a complete sentence or two, so I think that's good. Question C, in terms of theta, m, and any fundamental constants, derive an expression for the tension in the light string holding the box. I think you have to start with net force equals 0. We've done enough of these style problems to know that you're most likely to put your coordinate system aligned with the ramp, somehow like that. And that would align it with 2 of our forces if we exclude friction. If you didn't exclude friction and you were doing this last night, you might have said something like mg sine theta minus friction minus tension equals 0. So if you did it this way and had friction in there, I can see you doing it. So I'm trying to validate that if that's what you did. Unfortunately, this is static friction, which is less than or equal to mu times the normal force. So you couldn't do, say, normal force equals mg cosine theta and then did this substitution. That would be inappropriate because we don't know if we're at the maximum amount of friction or not, which is why this is, it's dubious that I would have had friction on there. So I really would expect that your answer looked like this. Tension equals mg sine theta, and that you just ignored friction. But if you didn't, then when you solve for this, if you had friction, it would look like that. Everybody understand the difference? No, I'm just moving tension to the other side of the problem there. Is that okay?
Yeah.
All right. does your expression in part C agree with your statement in part B? It sure does. Especially if you didn't have friction there, because as the angle gets bigger, sine of the angle gets bigger. Sine increases when theta increases. And if sine increases, then t increases. I do think you have to state something about the sine function increasing as theta increases. Because if it were the cosine function would decrease as theta increases. And look, guys, I can't do this anymore. Go sit down, or else I'm going to yelp in pain. So I just can't do it. I'm gonna be one way or the other. I've got a pinched nerve in my back, and it's giving me a lot of pain in my legs. Don't worry, I went to the doctor. They said I'm gonna be just fine. Maybe. Oh, God. So I'm gonna sit right here. I hope that's okay for you guys. Just give me a second. Moving right along. Does your expression in part C agree with your statement in part B? Yeah. Again, I do think you have to speak to the idea that sine gets bigger as the angle gets bigger. All right. The string is cut so that the box can slide without friction to section B, which is level, where the box now has velocity v. The box slides until it reaches section C, which does have friction. The friction in the is a. I don't think I would state all this any longer. That the friction is a percentage of the normal force. I would just tell you that there's a coefficient of friction. Does that make sense? We talked enough about it, so I wouldn't say all those things. I would just say there's a coefficient of friction, and I'd give you the symbol to use. Draw a free body diagram for the box as it slides along section B. I think that's weird. I probably said section C in class, but if you did B, the only forces acting would have been weight downwards and normal force upwards. So that's if it's in section B. If it's in section C, weight downwards, normal force upwards, and friction to the left. All right? So, again, we're going to push on the box in order to make sure the velocity stays constant, which is going to push on the box with a force that's something about the size of friction. Derive an expression for the size of the force necessary for part B in terms of V, M, mu, and any fundamental constants. Well, I don't know that V is going to be in our answer. This is a net force equals 0 problem. If I break this up into the x direction and the y direction, I'm going to have in the x direction whatever applied force and friction, that sums to be 0. And then the y direction, normal force and weight, and that equals 0. Now, I'm trying to figure out the applied force, and right now, all I got is F. That's not allowed in my answer, so I'm going to have to do some stuff to put it in the terms I'm allowed to have in my answer. So one of the things I do remember is that friction equals mu times the normal force. That would help work mu into the problem. I am allowed to have mu in my answer. So let's do substitution. The applied force equals mu times the normal force. However, I can't have normal force in my answer. But I can have M in my answer, and normal force equals weight. So normal force equals mg. That seems like a reasonable substitution. So my applied force will be mu mg. That's it. By the amount of writing I'm seeing out there, that seems like a few of you might have made a mistake here. But this one's pretty straightforward. So looking overall, I'm expecting probably an FRQ that's something like this, where there's not that many numbers, but it's mostly about being able to put together certain expressions. And if I asked about the acceleration on the frictional surface, net force in the x direction would have equaled ma. And the only force in the x direction maybe would have been friction. And if friction is mu mg, then you could have got something like this for the acceleration. About the same amount of work. Just instead of finding out how much force would be required to keep the box going at the same speed, we're finding how much force would be required, or sorry, how much acceleration you get if the friction is slowing the box down. All right?